This video we're going to talk about the effect of temperature on the rate of reaction. Like previous videos we have mentioned, there are 4 factors, and this video will focus on temperature. To study the effect of temperature on the rate of reactions, we have used these reactions. This reaction is very important, okay? You have to remember the reactions between the sodium thiosulfate and also the acid. So in the process, okay, the setup, it looked like this. You got a beaker right there. And then right below the beaker, okay, you got a paper. And this paper, okay, right on the top, on the center of the paper, you got a cross right there. So when you add thiosulfate in it, and afterward, okay, you add H+, the reaction will immediately start. At the very beginning, okay, because the solution is colorless, so you can clearly see the cross, okay, at the bottom of the beaker. But as time goes by, we've formed some sulfur. Sulfur, it is yellow solid. So as time goes by, more and more solid form in the solutions. And bit by bit, you'll find that the image of the cross, okay, at the bottom of the beakers will be slowly blurred, and at the end, okay, if we have sufficient yellow solid form, the cross, okay, will then be blown out, okay, by this insoluble sulfur, and we can't see the cross, okay, like this picture. So we'll describe the solution is turbid. So if we take the time, okay, from the very beginning that you add the acid in it, okay, till the time that you can't see the cross, the time spent, okay, for the reactions to form sufficient yellow sulfur to cover up the cross, that will be the time that we're measuring. The shorter the time we need to blow out the cross, the faster the reaction it is. You just imagine one of them, they take 10 seconds, the other one they need 50 seconds. So the 10-second one should have a faster reaction rate, while the 50 seconds, in order to form enough yellow solid to cover the cross, then that will be a slower reaction rate. So if you want to know about the details of the experiments, you can check this QR code. This is one of the very interesting experiments that we have in chemistry. Other than the yellow sulfur that we can observe, this will be one of the observations, very important. Other than that, okay, we also see that, okay, there is SO2 gas formation. So you have to notice that SO2 is toxic. So the whole experiments, we highly recommend you to carry out in film cupboard. And other than the yellow solid form, okay, you may also say that there is choking smell with burning sulfur can be detected because we have sulfur dioxide formed in the process. So the results, okay, it will be look like this. We can plot a graph which is called rate against time graph, okay. Normally it is concentration time graph, but this time, okay, we are using rate against time graph, okay, because as we have mentioned, the longer time it takes to blow out the cross, the slower the reaction. So actually the rate of reaction is inversely proportional to the time taken to blow out the cross, okay. So we can repeat the experiments at different temperature. So if we can do it at 22, 35, 45 like this way, at different temperature, we can see the time taken for the cross to blow out. We can see that, okay, at a higher temperature, the time that you use to blow out the cross, okay, you need shorter time to blow out. Shorter time means faster rate. So basically, we'll see that, okay, if the temperature is higher, the rate is higher. If the temperature is lower, the rate is lower. So by plotting 1/T, which is directly proportional to the average rate, against the temperature, because temperature, this one is the independent variable. And then the time taken to blow out the cross, this one is the dependent variable. We can convert it into rate. So we put rate as the y-intercept, okay, and then the independent variable, okay, which is the temperature right here. We can see that, okay, the higher the temperature, the higher the rate. The rate of reactions and temperature, they are directly proportional to each other, okay. So from here, okay, we can see that, okay, the average rate, okay, echo this one, is inversely proportional to the time taken to blow out the cross. Okay, but we can also see that higher temperature, higher the rate. So the results, okay, very obviously, just how we mentioned, higher temperature, higher rate. But one more thing I want you to draw your attention. This curve is not a straight line. It is an exponential curve. What means by that? Okay, you can have a look of these three data. One is 20 to 40. So 20, somewhere around here. Okay, 40, okay, somewhere here. And then 60, okay, will be here. So if we extend the graph a little bit here, then you can find that, okay, the rate, okay, it will be around 0.003. So from 20 to 40, actually you increase by 20 degrees Celsius, and the rate will be from 0.003 to 0.014. Okay, so therefore in the process, okay, you have increased 0.011. Okay, this will be the increase of the rate. But if we increase from 40 to 60, again this time actually we are also increased by 20 degrees Celsius. But this time, okay, we can see that the reading 40, actually it is around 0.014. 60 is almost 0.057. So in the process, okay, you can see that the increase, okay, it won't be 0.011 this time, but they will be like 0.043. Okay, so you can see that the increasing, okay, is much higher than, okay, from 20 degrees Celsius to 40 degrees Celsius. So we can conclude that the higher the temperature, the higher the rate it will increase. Okay, so basically the idea is when we increase the temperature, the reaction rate will increase a lot. Okay, so how can we use collision theory to explain the effect of temperature on reaction rate? So you can think about like this. This is a lower temperature situations. The particle inside the container will keep on moving and they will have chances to collide with each other. But when we increase the temperature, after we have increased the temperature, the particle, you will see that they will move faster. Okay, all of them, they have a longer tail. They move faster. If they move faster, they have more energy, they will have a more chance to collide with each other with sufficient energy. At that time, okay, more number of effective collision per unit time will be results, and at the end, that will bring up more higher rate, okay, for the overall reactions. So basically, the flow, okay, will be like this one. When the temperature increase, Ke of the particle will also increase. When they increase the kinetic energy, chance to collide with sufficient energy will also be increased. And at that time, more number of effective collision per unit time will be result, and at the end, the reaction rate will then be increased. So this is how we applied collision theory to explain the effect of temperature. So let's have a look of an examples. Okay, student, okay, right now is performing experiments to investigate the effect of temperature on the rate of reactions. So this time, okay, we have our bromine together with a methanoic acid here, and in the process, okay, they form Br- and H+ and CO2. So the progress was monitored by measuring, okay, the color intensity, the change in color intensity, okay, of the reaction mixture. Because this one is brown in color, these are colorless in color. Okay, so we measure the color intensity change with the colorimeter, okay, and then see what happens. Okay, first one, okay, you need to explain the change in color intensity of the reaction mixture. As I've mentioned just now, Br2 is brown in color, while the others one are colorless. Okay, so therefore, as time goes by, the change in color intensity, as time goes by, you'll see that, okay, the concentration decrease of Br2 decrease, so therefore the color intensity will also decrease with time. Okay, remember, color intensity will be related to the concentration. Concentration decrease, brown color will then be decreased. Okay, second one, okay, the experiment was carried out at different temperature in a water bath. Suggests how to get a temperature below about 10 degrees Celsius below room temperature. 10 degrees Celsius below room temperature. This question, you have to put a star for that. Because normally, if we want to increase temperature higher than room temperature, it's easy because we can just put that one, okay, under the Bunsen burner, and the Bunsen burner can help you to do the job. But if we want to have it below 10 degrees Celsius below the room temperature, then we may need to put some ice cubes, okay, in a water bath, and then we can immerse, okay, the reaction mixture in it until it falls about 10 degrees Celsius below the room temperature. So we can make use of the ice water bath to help us to do this. Okay, part C, in the diagram on the right, you're going to sketch the change in color intensity of the reaction mixture with a time at 15 degrees Celsius. Original is 25, now it's 15. So we'll know that the rates decrease. If the rates decrease, the slope, okay, will also be decreased. Okay, so to sketch a curve, okay, we'll have a curve like this. So you find that original one, okay, they may end somewhere here, okay, with the slope, okay, like this one, okay, very steep slope. But now we know that the slope, okay, or the rate will be slower. So therefore, we'll draw a less steep slope. As time goes by, less steep slope, and also you have to be end at a later time because, okay, the reaction is slowed down and the concentration of the reactant, it doesn't change. That means same amount of product have to be formed, but the reaction will be at a slower rate. So with these two tangents, okay, with draw and also a later time, we can now connect them together. So the slope, the new curve, okay, have to be like this way. Okay, remember, end later and also have a less steep slope. So finally, okay, part D, with reference to your answer in C, explain quantitatively, okay, the effect of decreasing temperature on the rate. Okay, so we're going to explain why temperature decrease, the rate will decrease. So basically, okay, like what we have mentioned, temperature decrease, the kinetic energy of particles decrease, then the chances to collide with sufficient energy will also decrease. So therefore, you have less number of effective collision per unit time. As a result, the rate will then be decreased. Okay, so more or less, okay, you can find these descriptions, okay, and the answer part D. Okay. So summary for these videos, okay, we've learned the effect of temperature on the rate of reactions. This reaction is very, very important, okay. Oh, forgot to mention one thing. This is a redox reaction, okay. I want you to notice that this S, actually it have a ON of positive 2. And this S have the positive 4. And this S have the ON 0. Okay, so you'll find that actually this S, okay, the ON, both increase and decrease in the reactions. So actually, this is another example of disproportionation. Okay, so the same reagents, okay, it add as the same chemical add as both OA and RA at the same time. Okay, so these reactions, okay, is very important, okay, because in the process they produce yellow solid, and this will bloat the cross, okay, right under the beakers. So the longer time it needs to bloat the cross, the slower the reaction. Okay, so remember, longer time, slower reaction. So if you have shorter time, 10 seconds, the cross disappear, then you have a faster reaction. So therefore, the time for it to bloat out will be inversely proportional to the average rate. Okay, so you have to learn how to plot a rate against temperature graph. This is a rate against temperature graph. Okay, so for the average rate here, okay, maybe you don't know the unit of it, but no worry, because this is rate, you can still use S-1 to help. So to explain in terms of collision theory, remember, temperature will affect the kinetic energy of the particle, and the particle with less kinetic energy, the chances to collide with sufficient energy will also be decreased. With less chance to collide with sufficient energy, the number of effective collision per unit time will also decrease. As a result, rate will then be decreased. Okay, so that's all for this video. Bye bye.